Kiểu em biết sao không, qua đi taxi đến đoạn gần về á, anh khúc trên đường về là anh đang nghĩ đến bài, tại ai cũng nói ốm, ai cũng nói bệnh, lúc đó 7 giờ mấy gần 8 giờ rồi. Anh đang định kiểu như than, gọi là than nghèo kẻ khổ để mai không phải làm bài đúng không, xong tự nhiên chưa kịp gì hết Tuyền nó bảo giáo sư ơi, yên tâm đi, chắc chắn là về tối nay em sẽ làm bài.
Mẹ nhà em đi ra giờ trước cửa rồi bà còn nói là nhớ làm rất là
Đó.
ai làm bà? Ủa gì hả?
Ông vậy là hiểu lầm.
Okay. Friday afternoon, we'd like to make sure that without too much of the rush or any rush at all, we can get forecasts by 4 o'clock or before 4 o'clock of the new Keynes and DSGE model. So let's embark on that journey to complete our DSGE model. First of all, right, we had discussed so far households and firms, and close out the description of the model by adding a monetary authority. That's per se, of course, going to set the central bank's monetary policy rate. But at the same time, as you'll see already from the notation on the left-hand side of 29, this authority also sets within our model the rate of return on those bonds. Right? Capital RT was the rate of return on the bond from T-1 into T. And so we do not distinguish here between the central bank's monetary policy rate and other interest rates in the market that are specifically applicable also to our one-period bonds. We think that that is all one rate of return. Of course, that's also for simplification at this point, and models that pay more close attention to the financial sector these days would also for sure have a risk premium and other distinguishing characteristics between a monetary policy rate and the interest rate at which households, firms can borrow, what is the bond rate of return in our market. So just that one interest rate applicable to the monetary policy, to the bonds, and what the central bank does do, it follows a so-called Taylor rule. Have you heard about the story where that name comes from in the Advanced Fundamentals of Macro?
We just know that it's Taylor rule, and you why
after John Taylor, a macroeconomist at Stanford, and in contrast to what's often casually reported, this is not based on some empirical evidence about what the Federal Reserve or another central bank would do. Rather, they had, in the time when he was in his academic prime, of course, they also had macroeconomic models, not the new Keynes and DSGE models or the like, but of course they also had macroeconomic models that were more based in the tradition of so-called Cowles Commission models that were dominant in the 70s, 80s, and probably in terms of practical policy, but also the 90s. Cowles Commission is an institute at the Yale University, where those classes of models came from that, in difference to these new Keynes and DSGE models, didn't have one overall framework, but took separate equation specifications from separate lines of reasoning. So in any way, they had this class of models, and then they also asked themselves which kind of monetary policy rule would maximize aggregate welfare, where welfare would be, of course, a particular function of the amount of consumption that individuals could afford over their lifetime. And so in such a model, they developed a rule that was not yet containing this lagged interest rate in 29, but the original Taylor rule is one that contained expected inflation and the deviation of output from potential output, that is the output gap. That turned out to be the awkward behavior of the central bank, And of course, within their model for given parameters, they could also determine what would be the optimal weight on inflation relative to output, right? How much priority would you want to give inflation targeting? Of course, behind this term here is the idea that the central bank has an inflation target, and when those inflation expectations deviate from the inflation target, that then the central bank would hike the monetary policy rate, right? Because if you hike the monetary policy rate, borrowing becomes more expensive for households and firms. There's less borrowing, less demand for consumption, less demand for investment, and so then we would expect that in such a situation, firms will produce less output. As less output is produced, there is more unemployment. And then finally, why does all of that help with the actual rate of inflation? If there's more unemployment, if you think about wage bargaining, but if you have more unemployment, then if employees vetted that they will quit their job if their wage wasn't being raised adequately, that is not such a strong threat to the employers, because they'll say, well, there's a lot of people out there who might retire. There's quite a few unemployed people out there, and I'd find quite readily a replacement worker for you. So we think that in times where demand falls, output falls, unemployment rises, there's going to be less wage growth, and if there's less wage growth, there'll be less price growth. That is inflation falls. And that's the mechanism, right, how we think that if the central bank is hiking the monetary policy rate, it will help the actual rate of inflation to come down. So that's the expected inflation motive in the Taylor rule, and the other one is an output stabilization motive that they might say, well, but we still want to give some consideration to actual output not being too far below potential output, and that if, however, that happened, that they would lower the monetary policy rate. If they lower the monetary policy rate, that lowers the cost of borrowing. That means more egg demand. If there's more egg demand, output is produced, unemployment falls, right? And so they stabilize, in that sense, the real demand. That's the intuitive reasoning for those two terms in the Taylor rule. But again, per se, those were coming from work that Taylor co-authors, colleagues did in trying to find the optimal behavior of a central bank to maximize welfare in terms of maximizing the present discounted value of lifetime consumption within the class of markets that they were working in at the time. Afterwards, it was found that if you actually take this Taylor rule with these two terms, in expected inflation, the output gap to the data, it actually can fit Federal Reserve behavior pretty well. So if you estimate those coefficients, phi pi, phi y, you can actually trace pretty well over time what was the evaluation of the monetary policy. When you estimate, however, you want to add this lagged interest rate, and that's why we also have it in 29, because if you think about what the Federal Reserve and other central banks do, they rarely ever would increase or decrease their monetary policy rate by half, let alone 1% or more. They want to do these adjustments of the monetary policy rate gradually, so that there's not too big of a shock to financial markets, because they're afraid, right, if they hike, for example, the monetary policy rate in a big step, that financial markets would become extremely concerned that this would lead to a huge slowdown of economic activity. They would lead to a sell-off of stocks in the stock market, and this could cause quite some undesired volatility, perhaps even financial instability. So they adjust slowly. And how do you get that? If you put a relatively large weight on the lagged interest rate, right, then you make sure that today's interest rate is not too far away from yesterday's interest rate, right? And so that way you make sure that even in the terms of expected inflation and the output gap, which suggests a relatively large adjustment of the monetary policy rate, it doesn't happen, because the central bank also says I care about yesterday's rate, and again the larger row, of course, larger between values of 0 and 1, the closer it is to 1, the larger that value, the smaller everything else equal, the changes in the monetary policy. VT is the monetary policy shock. So now we have 3 shocks, right? We have beyond the technology shock, the preference shock, and now we also have monetary policy shock. And of course, as we just discussed, monetary policy affects the demand side, right? It affects the borrowing costs, consumption, investment demand, and in an open economy, it would of course also affect the demand for imports. And so this V is another demand shock. Right? So we have a second demand shock in the model, and that is here modeled as a first order regressive process as well. Same comments as in the morning. Don't read too much into one being included in the support of rho V. We will typically think of this monetary policy shock as being a stationary process. Of course, in our early language, again, the monetary policy shock is itself an epsilon V. It's just like for the technology shock in the business cycle models. That's a bit that casual language that when people talk about the monetary policy shock, they often mean the whole first order process in V. That's the one to avoid. So at this point, we have 3 core equations in consumption, in inflation, and in the interest rate. It's not going to stay, however, a model in consumption, inflation, and interest rate, because in this model, what is the counterpart to our egg supply equal to egg demand constraint in the business cycle model? In the business cycle model, we had investment, right? That households and firms could also buy physical capital. Not so anymore in this model, right? We don't have physical capital. We didn't have a government sector in the real business cycle model. We don't have it here in terms of at least expenditure in goods and services. If you think of the one authorities, stream partners, public sector, okay, but usually, right, central banks, at least in economies in Europe, in the US, they are rather independent of the public sector. It's a separate institutional entity. But one way or the other, right, there's no government expenditure, there's no exports, no imports, and once more, no investment in physical capital. So output is equal to consumption. And if you say, well, that's too simplistic, I had a model in intermediate macroeconomics at the regional level that did more than that. I'm not doubting it, but we probably didn't have intertemporal optimization problems that derived each and every decision rule in a consistent manner, right? It sacrificed that at the cost of a lot of other things, probably including dynamics, including a stochastic environment. So that's this world, right? And so what used to be the Euler equation for consumption, because y is equal to c, if you just plug in y for c, now becomes what we call the dynamic IS curve. Intermediate macro says what? Intermediate macro says for the IS curve that output is a negative function of the real interest rate, right? That's the standard undergraduate macro model that you plot an IS curve. The S curve on the horizontal axis has output, on the vertical axis has the real interest rate, and then you have a downward sloping IS curve. Well, of course, again, this mechanism that as you have a higher cost of borrowing, you have less demand, firms produce less, output falls. Right, and that's in this curve too. White is a negative function of the real interest rate, but also a function of the preference shifter and a function of expected future output. And that's why we call it a dynamic IS curve, because it has this dynamic element in expected future output. That's not in an undergraduate macroeconomics model. It's typically not. But here we have it, right? So this is not a static model anymore, it's a dynamic model, but it still resembles a great deal the IS curve from undergraduate macroeconomics because it contains that core dependence of the level of output on the demand side on the real interest rate in a negative form. Nominal interest rate minus expected inflation minus the real interest rate, so this is negatively attractive output, just like in the S curve, but we have this additional term in future output. That's one curve, right? Then we had before an equation in the rate of inflation in 28. So again, without doing all the algebra, if you plug back in all those optimality conditions on the firm side, demand for the factor of production, labor, aggregating across the output from the immediate goods producing firms, taking down the cost structure in the immediate goods producing sector. Let's write some algebra. And this one I wouldn't necessarily suggest, even if the algebra is blind, I wouldn't necessarily suggest try to divide 33 from 28 and the other optimality conditions in the firm sector. This is a bit super tedious. So what it gives, however, is also a second equation in the rate of inflation as a function of the output gap. Right? Last time on the right hand side is the output gap, so it gives us inflation as a function of the output gap. Now, if you replace the output gap by unemployment, deviation from the natural rate of unemployment, what is that curve called in undergraduate macroeconomics? The Phillips curve. Right? That's the Phillips curve. The Phillips curve suggests, in terms of output, formulated in terms of output, the larger the actual level of output, the lower the rate of unemployment. The lower the rate of unemployment, the more power at the wage bargaining table to the employees, right? Because if unemployment is very low and the firms say, you guys are dismissed, we'll just find replacement workers, that's getting ever more difficult for a firm as unemployment is very low. So as output rises, unemployment falls, wage growth does increase, and if wage growth increases, the cost of production for the firm increases. Remember, firms charge prices that are marked up on their costs, so if the costs fall, for sure they increase their price growth, the rate of inflation increases. That's the standard Phillips curve. Now here again you have another term, that you don't have an undergraduate macroeconomics, you have the expected future inflation. And that's why we call this either a dynamic Phillips curve or a forward-looking Phillips curve or a new Keynesian Phillips curve. But in essence, right, if you compare the structure to an undergraduate model, at this point we have beyond the IS curve what in undergraduate macroeconomic model you would call the aggregate supply. Yes, right? That's the supply curve is another label for the Phillips curve, that upward sloping relationship between output and inflation. And again, the mechanism as output increases, you have lower unemployment, you have higher wage growth, and as you have higher wage growth, you have higher price growth. Now, which curve is still missing? From the perspective of undergraduate macroeconomics, what curve do I need to fill in? Just one more, you might say two, but I would insist one. I'll explain in a second why. Which curve is still missing? I would call it a Taylor rule curve. I think Professor Aliassos refers to still call it the Taylor curve. Now, what is the aggregate demand curve? The combination of the S curve and the TR curve, right? So once I have the TR curve, I have the whole undergraduate model. And of course, I have the market policy rule from 29. Right? So a three-equation model, very different in terms of derivation from ISTR, ISLM, and ASAD. But at the end of the day, it's the same set of equations within a framework that's containing intertable optimization in an uncertain world, and when all equations come from one overall microfounded setup rather than pieced together individually. Right, and so it's surely very different than undergraduate macroeconomics, no doubt, but the core set of equations, the three equations that we have in this new Bayes and DSGE model, all has its counterpart, all have their counterparts in undergraduate macroeconomics, IS, TR, and supply, and again, once you have IS and TR, we also have demand. So we have the full demand. But the difference is we have these future expectations, and that we talked already about before we started the lunch break, right? That now we have to find a way to solve out these future expectations as a function of observed variables. Because we want to bring this model to the data, it better be an observable structure. Because you could say, let's do something very complicated, we have an unobserved component structure for something, but at the end of the day, this will always need to come down to a way to solving up these unobserved future expectations as a function of observed. And that's, again, because such conditional expectations are in macroeconomics called rational expectations, called a rationalizations model that we want to solve. In 34, we have the general form of it. That's just collected from our setup. Right? If you went to our setup with the third equation being the monetary policy rule, the second equation being that Newton-Phillips curve, and the first equation being our dynamic IS curve, right? You could plug from 32, yt as a function of expected future, y, expected future pi, plus the exogenous term in z, from 33, pi as a function of expected future inflation, and the output gap, as well as the monetary policy rule in 29, interest rate as a function of a lag interest rate, expected future inflation, and the current output gap, you can plug back into that matrix formulation. Right? 35, 36, 37, 38 is the definition of the matrices in 34. Let's just take out one equation. If you say I'm not yet seeing the connection, well, let's take the first equation from here. M00 says 1 times yt, right? 1 times yt, plus 0 times pi t, plus 1 times rt, is equal to, we call M01 is the coefficient matrix on yt minus 1. So that is equal to one times yt plus 1 times pi t
Expectation.
No, there's no typo. I've just copied one from the whiteboard, right? So M01 is the coefficient matrix on expected value t of yt plus 1, whereas M10 is the coefficient matrix on yt minus 1. All right, so with that correctly in mind, let's redo the right hand side. So we have 0 times yt minus 1 plus 0 times pt minus 1 plus 0 times rt minus 1. And now come those terms in the expected, one step ahead expected term. That is equal to 1 times expected value at t of yt plus 1 plus the expected value at t of I t plus 1. Likewise, in the second equation, I have minus kappa times yt plus 1 times pi t equal to, again, the second row here, right, it's just a row of zeros. So plus beta times expected value at t of inflation t plus 1. The third equation reads minus phi y times yt plus 1 times rt equal to, now we have this row, right, that's on rt minus 1. Plus pi times the expected value t of pi t plus 1. Right, and of course now I still don't have my terms in exogenous entries, so that's in wt tilde. That's defined on slide 21. And so to the first equation I need to add plus 1 minus rho z times zt minus rho. The second equation I need to add minus kappa times y potential. And to the third equation I need to add plus vt minus phi y times y. But if you compare that back to our optimality conditions, we had for Taylor rule RT is equal to rho RT minus 1 plus phi pi times expected value t of pi t plus 1 plus phi y times yt, bring that to the left hand side, phi y times yt minus phi y subscript there times y potential. Last week. Right, so the last equation definitely is my Taylor rule. The equation in inflation from 33, right, is pi t is equal to beta times expected value t of pi t plus 1. Kappa, I just call this whole term in 1 minus theta times 1 minus beta, theta times 1 plus phi divided by theta. This is now my kappa. Minus kappa on it. And then this just Yeah, okay, sure. I bring this kappa from the left-hand side to the right-hand side, right, and that's consistent with 34. I'll just bring that to the other side. Then we have 33. And then finally we still need our dynamic IS curve. YT equal to the expected value of t of yt plus 1 minus rt, bring that to the other side, minus minus is a plus, right? So plus the expected value of t of yt plus 1, plus 1 minus rho z times z minus 1. Right, so I've just rewritten our three equations in the form of the equation system in 34, with the matrices defined in 35, 36, 37. The vector y, if you think this is a bit unfortunate notation, maybe because we have within y output, which is y, but I just want to conform to general notation that people use in such a REST notations model, and they usually use the same notation as in the VR. We remember in the VR, right, all the enormous values were in the vector y. That's why I want to have this vector y here, but of course it contains as one element the scalar variable output, right? And again, the exogenous variables in our shocks to preferences, shocks to market policy on Z and V, and these are additional terms that I here in the setup treat as constant, potential output treated as constant. When we later bring it to the data, we can certainly allow for time varying potential output series and have potential output varying with time as well. Now, if you look at M00, you'll see right away, right, if you take the determinant of M00, this is 1, 1, 1, 1 minus minus plus phi 1 times 1 times 1, the term is 1 plus phi 1. Unless phi 1 was equal to minus 1, which would make no economic sense whatsoever, right? Because again, this is coming from the one policy rule. You don't want to have a negative coefficient. That as you have more output, the central bank will lower the one positive. Completely nonsensical economically, right? So we can rule that out, that phi y is equal to minus 1, and therefore we can invert that matrix M00 and write the whole thing in the form of 4. And now it looks yet a bit closer to a VR, except we still have these unobserved expectations at time t about future values of y t plus 1. And so we still can't treat this like a VR now, so let's go ahead and estimate it because we don't have data on the expected value of y t plus 1. We still need to solve that out. So yesterday Danair did that for us in the real business cycle model. I didn't talk about it, I just said let's focus on the intuition as to how this model generates business cycles, but today I don't want to say let's just leave it as a black box, because this is the essential step. Right? Once we have solved out these future expectations, we'll see we're back to a VR type model, just with lots of boundary instructions. But so this is the essential step. I can't just skip on it. So I want to discuss with you explicitly how to solve this model. I'm not sure why my laptop is again running back and forth on its own. And I should disclose in this context that what I'm discussing with you there is a solution method for this class of models. That I have a vested interest in, because it comes from work of mine with with Harsha Pesseran. I'd love to talk about this all day, because we're still actually now together with Alex Margode, who will teach you in September this course on macrofinance models. We're still working on some solutions, refining them. This is indeed 1995, so I guess now I have to say what I learned from lunch. According to Vietnamese culture, I'm in my 80s. I can't hide the fact that I wrote a paper at that time. No, just for those of you who were in the lunch. One of you was vastly overstating, let's keep it completely neutral, his or her age. So I learned that that is the polite way to do it. So in that sense, I'd say from this one, assumed in 1995, I was in my 60s, and then I would be in my 90s now. Also, whatever, right? So anyway, this is a while ago, but again, this is actually not just research from ages ago, but there's still ongoing work in this literature to try to make such solutions get more accurate, refine the computational time and so on. That I'll not focus on here today, but just give you the core idea how this method goes about solving these models. And so maybe as a small intermediate step, right, why is this requiring some further thought to solve such a model? Well, if I thought about special cases, if B was equal to the zero matrix, we don't need to talk about the solution, right? Because if B is a zero matrix, this will be R in essence. Almost, because we might say W itself contains only a one component, but it looks like a BR, right? So then we did not have any need for any discussion how to solve this model. And also the special case where A was equal to 0, it would actually be rather straightforward to solve this model, right? Then the model would be yt equal to B times the expected value at the t of yt plus 1 plus wt. How could I solve that model without huge effort? Suppose all eigenvalues of B are less than 1 in absolute value, and do the following. Plug in for yt plus 1. What must be yt plus 1? Yt plus 1, if I shift all time scripts 1 time period forward, must be equal to B times the expected value at t plus 1 of yt plus 2 plus wt plus 1. And at this point, I just have shifted all time subscripts 1 period forward. Now plug back in, right? Plug back in. What do I obtain? Yt is equal to B times the expected value at t of B times the expected value at t plus 1 of yt plus 2 plus wt plus 1 plus w. Now, what is that? B is at this point a known matrix, right? We think we're in population, so that's B squared. What's the expected value at t of the expected value in t plus 1 of yt plus 2? The iterated expectation, right? And so, if I think today, right, about what I know tomorrow or next period, unless I'm forgetful and we are rational agents, right? So they're not forgetful. They remember everything next period that they knew today, but they don't know yet today the extra information that they will have tomorrow. Right? So this is indeed what they know today. That's a so-called law of iterative expectations. Et of yt plus 2 plus b times the expected value t of w t plus 1 plus w. At this point, you have done so many of these recursions that I conjecture you can already see the pattern after one go, right? What is the pattern? If I have further steps forward, so I to the expected value t of yt plus h. What is b going to be the coefficient on it? B, yt plus 1, b squared yt plus 2, b to the power of h times the expected value t of yt plus h plus sum s equals 0 to h minus 1, b to the power of s times the expected value at t of w t plus s. Take the limit as h tends to infinity. B, per assumption, has all eigenvalues inside the circle, less than 1 in absolute value. This converges b to the power of h and limit as h tends to infinity to 0. So this is sum s equals 0 to infinity b to the power of s times expected value t of wt plus s. Now, we might say, well, this book contains unobserved conditional expectations. But what is W? Exogenous. Let's just suppose, right, that WT was overall this first order all-regressive process. What is this equal to? Sum s equals 0 to infinity, b to the power of s times. We have done that. We know that. Et of wt plus s under such a first order all-regressive process is r to the power of s times w. And because all these expected future shocks are in expectation equal to the unconditional mean Western R. Right, so now I have yt as a function of observance. But only in that special case where A was the zero matrix. Now, feel free to try on your own. If you plug back in a non-zero A matrix and did such a forward recursion, you're never going to get rid of these future expectations, right? Because these backward terms shift into the future. So you can't do this anymore when A is not the zero matrix. And that motivates the solution method. Again, a press one in mind, where we said, well, let's try to decompose the model into a backward part. The backward part is like b is equal to 0, but of course without setting b is equal to 0, right? Because we don't want to do that. We want to solve it for non-zero. But let's have one backward part. That's like a VR. We know how to solve this, right? And let's have a forward part, because if we had a forward part, at least for now in the case where all eigenvalues of b were less than 1, we can discuss other cases later, we know how to solve it without too much trouble. So if we found such a decomposition of y into its backward part, backward solution, and the forward solution, then we should be able to solve it. How did we define it? We define a vector capital Y that's defined to be our vector YT, right? YT is, in our notation, output, inflation, interest rate. The vector of endogenous variables define capital YT as the vector of endogenous variables, lowercase yt minus c, yt minus 1. Where at this point we don't know the matrix C. It is yet to be determined. And that's the job. That will have to determine, in part, this matrix C. And we'll see in a minute how. But let's suppose we find a way to calculate this matrix C. Right, then we can certainly define capital YT. Capital YT is going to be the forward part of the solution, and the C times lowercase yt minus 1, the backward part, right? Because of course, trivially, if you add up here, the backward part and the forward part, what is ytb plus ytf? C lowercase yt minus 1 plus uppercase yt, which is equal to yt minus c yt minus 1. Right, so of course, if I add up backward and forward part, I have my endogenous vector y. So if I find the matrix C, in short, I can calculate capital Y. Therefore, I can calculate the forward part. I can, with the matrix C, always also calculate the backward part, and adding them up together gives me my vector lowercase y. Okay, but now we have to find that matrix C. Where are we going to get it from? Do the following. Substitute from 44. Remember, 44 was our definition that capital Y is equal to lowercase yt minus c yt minus 1. Therefore, of course, right, what we want to keep in mind also is, maybe let me put that in red to help our memory. We have that lowercase yt, right, so maybe here you can see all yt, right, from the definition in 44, is equal to capital YT plus C lowercase yt minus 1. Plug that into our original model, right? Keep in mind the original model is in 40. Right? I plug into 40 for lowercase y from this definition. Uppercase yt plus C times lowercase yt minus 1. So what do I get? On the left-hand side, I get uppercase yt plus c lowercase yt minus 1. On the right-hand side, I keep the term in lowercase yt minus 1. It's predetermined, right? I don't need to solve out for that. Plus b times expected value at t of lowercase yt plus 1. What is lowercase yt plus 1? If I just shift the time subscripts, one period forward, lowercase yt plus 1 is of course uppercase yt plus 1 plus c lowercase yt. So I plug that in here. Uppercase yt plus 1 plus c lowercase yt plus wt. Now I'm still not happy with that because this now contains, again, y, lowercase at t. So I have to plug that in one more time for lowercase y at time t. And of course, lowercase y times t is uppercase y at time t, right? bc times uppercase yt plus bc times c bc squared yt minus 1, lowercase yt. Now collect terms. On the left-hand side, collect terms in uppercase yt. I have I, the identity matrix, times uppercase yt, that's this term here. Right, minus bc, uppercase yt, takes this term to the left, On the right hand side, what do I have? BC squared, lowercase yt minus 1, plus A, lowercase yt minus 1, and from the left hand side A, minus C, lowercase yt minus 1, plus the term in B, expected value T of uppercase yt plus 1, plus W. When was it successful that, as we wished, uppercase Y would be the forward part of the solution? When is uppercase Y purely forward-looking? Look at 48. When is uppercase Y purely forward-looking? Capital Y or uppercase Y T as a function of, we expect whether T of uppercase Y T plus 1 plus exogenous stuff, if this term cancels out. So what is my condition on the matrix C? BC squared minus C plus A is equal to 0. A quadratic matrix equation, right? Because it's quadratic in C. C is the unknown. I have as an unknown a quadratic matrix equation. And if it helps you for your future research, at the time when we did this, people said, this is weird, this is strange, nobody has ever converted the solution of such a model into a quadratic matrix equation. That was 95. If you ask in September, Professor Meyer-Bode, what does a wedge computations model solution boil down to? People say, well, of course, a quadratic matrix equation. Now everybody thinks of this in the form of a quadratic matrix. At least many people don't have it, but many people think of this as the solution of the quadratic matrix. So if you think it's weird, in 1995, everybody would have agreed with you. Today, not that many anymore. They would say that's natural. That this boils down to the solution of the quadratic matrix. Now, maybe you haven't seen quadratic matrix equations before. I suspect you haven't. But you say, well, but I've seen quadratic equations in the scalar setting. But recall, for example, of course, the product of matrices doesn't in general commute, right? The matrix A times B, even if it was of such dimension, say squared, that B times A also was well defined. B times B is certainly not B times A. Right? And so you cannot apply a quadratic formula to a matrix set. Doesn't work. And that's where the work continues until today, that there's still some disagreement how to numerically solve best this quadratic equation in C. What we'll do here, within the course, within the programs that I've already put on the course website, we'll do a recursive procedure. That's in 50. Where does that come from? If I write this in red, well, I can write right into the middle, and you still know where I am. Right, so this, if you write this quadratic matrix equation in 49, in the form of B times C minus I times C. Right? Then this is still BC squared minus C plus A is equal to 0. But of course, you can now also write this as C is equal to BC minus I inverse times A with A minus sign. In front of that, and of course with the minus in front of it, this is the same as 50 I minus B times A. Now you say, well, C is both on the left and the right hand side, how can that be helping us to solve for C? This suggests an iterative procedure. Right? Conject an initial guess for C, plug in an initial guess, get your new value for the C matrix, plug that back in as your new initial guess, get another value of C. Iterate until this converges. If you said at this point, I'm not sure whether this is going to converge, yes, but it will work extremely well, and we'll not to discuss today underlying work in the numerical linear algebra literature that can explain to us why this is going to converge, at least under certain conditions. That's too much math, we'll not sidestep into that. All right, suppose we have our matrix C. Right? We seem to be almost there, but not quite. Right? Because now let's think about the forward part. The pure forward part is in from 48. Capital YT, we need to pre-multiply on both sides by I minus B times C inverse. Right? So if this is 0, because the quadratic equation is 0, I minus B times C inverse, pre-multiplying B times the expected value T of capital YT plus 1. And that's what I have here. And we'll call that matrix I minus B times C inverse times B, hence will be F matrix. Just short simplification. Plus, of course, right, the last term pre-multiplied by I minus B times the inverse, also need to pre-multiply W by I minus B times the inverse, and just to have more compact notation for that too, I'll call that capital W. So in compact notation, what do I now have? Capital Y t is equal to F times the expected value T of capital Y t plus 1 plus W. And what do I do in 52? Just do the same thing as we did here on the whiteboard before. Right? If it's purely forward-looking, at least in the case where all eigenvalues of F are less than 1 in absolute value, I can solve forward. In the limit, the corresponding part on yt plus s, or yt plus h, as h tends to infinity, goes to 0. I only have these conditional expectations and exhaustion stuff left, and at the end I just plug back in for capital W. Right, capital W is I minus B times the inverse times lowercase w. Okay, this is exhaustion stuff, so if I plugged in an AR1, right, that has solved out fully the other side. So in the case where all eigenvalues of F fall inside the circle, if I piece everything together, remember yt, in terms of the vector y, that is our endogenous variables vector that we want to solve for initially, that we have decomposed into the backward and the forward part. Plug in the backward part first. Lowercase yt is equal to c, lowercase yt minus 1. That's the first part on the right-hand side of 53. And what do I need to add to that? The forward part. Right, and the forward part is defined in 46. It's just the solution of uppercase yt, capital YT, and that we have just found in 52. So add that, and we have our solution for lowercase yt. Again, you may say, well, still I have those huge expectations in W, but this is exogenous, plug in AR1 and R mark PQ, whatever is your model for exogenous values, you have the solution. At this point, still a bit incomplete, because it rests on the assumption that all eigenvalues of F fall inside the unit circle. And as I'll show you, when we'll take our three-equation model to MATLAB, this is not necessarily true for economically sensible values. It may, unfortunately, from the perspective of causing additional work, unfortunately, not from the perspective of economic insight. So unfortunately, it is very possible that some eigenvalues of this matrix F fall outside the unit circle. Now, let's do, therefore, the extremum case. And the immediate cases will be on the problem set, where some eigenvalues are inside the circle, some eigenvalues are outside the circle. Decompose the system into the two parts, one inside, one outside. At the end, plug it all back together again. But for now, I focus on the other extreme, right? Where rather than all eigenvalues have inside the circle, they're all outside the circle. And don't think this is going to be, again, just a technicality. My hunch is, we'll check once we have the solution, you'll be stunned what the solution is in this case. So let's work. Right? If all eigenvalues of f fall outside the unit circle, I definitely cannot solve forward anymore, right? Because what happens to f to the power of, in this notation, I, as I tends to infinity, if all eigenvalues of f fall outside the unit circle, goes up. Right? This is not a sensible solution. I can't do that. So I have to do something different. Well, if all eigenvalues of f fall outside the circle, f to the power of I, as I tends to infinity, what does f to the power of minus I tend to?
Zero.
Zero, right? Because the eigenvalues of f inverse will all be inside the unit circle if the eigenvalues of f are all outside the unit circle. So we want to solve backwards. And how do we do it backwards? Well, the trick is we plug in for this expected value at t of capital YT plus 1 in terms of the realization of capital Y time t and the realization of this exhaustion. Right? This representation 54 comes immediately from our forward system in 51. If I solve for the expected value at t of capital YT plus 1, this is equal to f inverse times yt minus f inverse times capital wt. Now, how can I relate that? Now, if I now want to solve this backward, that's going to work. But the problem is on the left-hand side, I don't have capital YT plus 1. On the left-hand side, I have the expected value at t of capital YT plus 1. But I don't want to have that, right? I want to have capital YT plus 1 because I want to solve for capital Y to plug that into my solution. So 55 uses a property of conditional expectations. Namely, that I can decompose the expected value at t of my vector uppercase y times t plus 1 into the actual value of uppercase y times t plus 1 minus xi t plus 1. What must be the property of xi t plus 1? Well, let's just calculate from 55, right? What must be the expected value at t of xi t plus 1? Must be equal to expected value at t of uppercase yt plus 1 minus expected value at t of expected value at t of uppercase yt plus 1, which of course is the expected value at t of uppercase yt plus 1, right? So this is 0. The one step ahead expectation of uppercase psi t plus 1 is a 0 vector. You may have heard the term of Professor Hassler, I'm not sure, but you may have heard it, martingale. This is a martingale difference. Because what is a martingale process? A process for which the one step ahead expectation is the value of the process today. Right? Just like our random walk. Random walk is an example of a martingale. A martingale difference is a process for which the one step ahead expectation is the 0 vector. And that's exactly what it is, right? From 56. So, excuse me, xi t plus 1 is a martingale difference process. But if we use that, right, if we use 55, we can rewrite 54 as substituting also back one period, right? We don't want to have all of this in terms of y t plus 1, we want to solve for capital Y time t. Capital Y at time t is equal to, now I need to shift all the time subscripts one period backward, f inverse uppercase yt minus 1 minus f inverse uppercase wt minus 1. And of course, this thing, right, goes to the right-hand side, so plus that martingale difference vector xi at time t. Now I have a model that I can solve recursively backward, right, because it's in F inverse. And all eigenvalues of F fall outside of the circle, so as I solve backward, F to the minus I, as I tends to infinity, again converges to the zero matrix. We do that on the next slide. We solve that recursively backward. Looks a bit imposing, right? But this is exactly like when you solve the VAR recursively backward. Nothing different. Just plug everything in. And in the limit, this must be equal to, if you plug back in for capital W, in terms of lowercase w, right? Remember that was defined in 51. Uppercase w is a function of lowercase w. You plug back in also that definition from 51. You have that uppercase yt is solving backwards as a function of lag w's, wt minus 1, wt minus 2, wt minus 3, and so forth, plus a function of the martingale differences, that t minus 1, t minus 2, t minus 3. Let me get to the overall solution before I interpret it. Right now, plug back in for uppercase yt is equal to lowercase yt minus c lowercase yt minus 1. That is, add to the backward solution in quotes the solution of the forward system. Even though we solved it backward, I can still call it the solution of the forward system and have 59. And 59 at first would seem fine, right? Because it says capital Y is a function of, lowercase y is a function of lowercase yt minus 1, backward looking part, like in a VR, and stuff in lag exogenous vectors. Wt minus 1, Wt minus 2, Wt minus 3. So far, so good. But in the solution, we also have these current and lag martingale differences. And what do we know about these martingale differences from our new Keynesian DSGE model? Not much. All that we know is the one step ahead expectation is the zero. Any process for which the one step ahead expectation is the zero vector can be part of the solution in 15. So some people call this type of solution a so-called sunspot solution. How can that be? We talked about new Keynesian DSGE models, we talked about business cycles. Why do we now switch to sunspots? What people mean by that is something completely extraneous could matter. And I don't think they literally mean sunspots, but if we have to interpret literally like sunspots, right, that we all go to the window at night and try to see sunspots. And if we see some, we say, bad, bad, bad. The world is going bad, bad, bad. Let's stop consuming, let's stop investing. We're going to run into a recession. Just because we looked out of the window and saw some sunspots in the sun. Right? That's the idea. There's extraneous factors, like in Keynes' general theory, right? He already talked about these fickle investors. Investors who are not basing their expectations on fundamentals of dividends and whatever it may be, but they base it on what does this guy think? And maybe that could be important what that guy thinks. Or there's some other technical trading rule that they just see somewhere in the stars or wherever, and then they buy or they sell. Right? Extraneous factors, market psychology, all that could matter. Now I'm not saying it does, right? Because these sunspots may not be there. These could be martingale differences that are martingale differences in functions of the fundamentals. Could be. We don't know. We just don't know. In that sense, it could be a function of the fundamentals, this martingale difference, but it could be a function of any extraneous factor, whether it's market psychology, sunspots, and so on. And in that sense, I was predicting that you'd be stunned. I'm not sure, are you? Or you said, yeah, sure, absolutely. That's what it should be. Have you seen such a model with an infinite number of solutions before? There's an infinite number of solutions. Because there's infinitely many stochastic processes that will satisfy the requirement of being a martingale difference. I'd find it, if I saw it the first time, I would still think I would find this stunning. But it's also real world. Just to tell you one real world story where this actually showed up in professional practice. Some years ago, when in the context of the European sovereign debt crisis, the European Central Bank, just like the Federal Reserve before, brought the monetary policy rate in the euro area down to 0. In Germany, a lot of people were very upset. Among them, German economics professors, some of them were very upset because they felt this is so different from what they had been teaching for decades, how the German Bundesbank controls money supply. And of course, if you have an interest rate of 0, right, this could mean an enormous extension of liquidity. So they were upset about it. Also, some financial market participants were very upset because they said, our savings account, we get 0 interest these days on the savings account. This can't be true. Why are we not rewarded anymore for putting money in the savings account? Because in Germany, this is particularly common that lots of savers do not want to invest in stocks, do not want to invest in other risky assets. They want to put their funds into a savings account at their bank. In addition to a checking account, have a savings account, because why? Unless the bank was to go bankrupt, which is very unlikely, and if it was to go bankrupt, there's an insurance scheme that up to, I think, €100,000 covers all losses that an individual saver would have if the bank went bankrupt. So it's safe. It's safe if you save in the saving account, at least as long as it's less than €100,000. And so people love it because they think it's riskless. It's not really riskless because the interest rate is always nominal, and you never know the real return ex ante either. But I guess some people don't see that there's still some risk in it. Anyway, they think of savings as a safe thing. So they were also upset that when the European Central Bank went to a 0 monetary policy rate, they had no return in what it seems. They also went to court. So in short, this went all the way up to the German Constitutional Court, and those judges, what do we know about monetary policy? We are experts in law, but we are not experts in monetary policy. So whereas it's customary for such cases, they invited experts to come in to inform them about, is this a justifiable policy of the European Central Bank that it would bring that monetary policy rate down to 0? And so then one expert whose name I already gave you yesterday in the context of tricks, how to log linearize models, Uli came in and was one of the experts, and he said, well, macroeconomic models can have multiple equilibria. And so it's impossible to judge whether this or that path of monetary policy leads to this or that outcome. But there's too much uncertainty, because the solution of the model, the macroeconomic model that's underlying the monetary policy, we have multiple equilibria. And so he said, I can't you say, I know that the European Central Bank does something very wrong. I can't look into judges' brains, but in the end, they certainly rejected that the lawsuit that the European Central Bank would have to be forced to abandon the zero-low bond regime and induce positive interest rates that they charge the commercial banks and borrowing from them, and therefore the commercial banks also having non-zero positive interest rates when offering savings accounts to savers. So in that sense, such models have to be real world. They certainly have been argued in front of highly important proceedings, in front of courts of law that decide upon my policy issues. So in that sense, this is not just an abstraction, but once more also in the mark. I'll show you as soon as you go to MATLAB this case that some eigenvalues of f are larger than 1 canonized. And we'll see exactly in which kind of settings this may be particularly likely. So if you give me just a few more minutes, maybe not just until half past, but maybe until 35 or so, let's illustrate it in that. And all these calculations that we have just done on pen and paper, because in practice, of course, right, it's about how does this work? Can we actually solve the one that we want to work with here and bring it into a form that we can typically do. So I go to MATLAB, and on the course website, you have a file, MLRE, solution illustration, new case in DSGE.m. The first file, I'm connected here. I am. So the first file after this rbc.log file that we had yesterday, please download that and put it into your working directory in MATLAB. Again, crucial that you put it into your working directory. If you followed my setting of working directories, I'd recall that I would put my working directory as C, where is it? As C MATLAB 18F25. You can choose another working directory, but please put it there. Make that directory to be sure to be included in your MATLAB path, and also make it a working directory here within your command window. Then all of this will work. And so let's illustrate that a bit. Font size is a little bit too big, so this is 25B. They have shifted around the menu a little bit. So where's the font size? Before we found out. Render the smaller font size so that we see the whole text on one screen. And in 25A, I'm just not sure now where they put that command that we can adjust the font size of the windows within this data. View?
The zoom next to the extent, to the left of the extent. That's all the way here. Yeah, like around the middle. And like look to the.
Oh, those.
Yeah.
Oh, okay. Do you also know whether they still have a command where you can choose the font and the font size? Should be somewhere, right? But this one, I mean, let's just continue with that. Zooming out. So now we see the whole thing on the screen, and maybe we can zoom out yet a little bit more so that I see a bit more also vertically. So we are in the MATLAB M file editor. I start again with some context at the top, right? So this was the percentage sign. Also in the Linear file yesterday, that's just text. Do the housekeeping, to clean up the memory, clear up the command window. Then I provide values of the parameters. Where are those coming from? Values that are often frequently used in the literature. Later we will still estimate all of these parameters, right? So let's initially just say that in particular I have one policy rule where the coefficient on the leg interest rate is 0.8, the rate on output in the Taylor rule is 1, and relative to that, the rate on expected inflation is more than 7.5 times as much, the rate on output. I enter the model, right? Recall we had these M00, M01, M10 matrices, and just double check it, right? That all these entries here are as in the slides, and we confirm that if they're in the slides, as in the slides, this gives us our original model equations. So I enter those matrices, and then I calculate the A and the B matrices. Please recall the A and the B matrices, right? They were defined in 41 and 42, right? A is M0 inverse times M10, B is M0 inverse times M01. So also calculate these A and B matrices in lines 41 and 42. Now I want to calculate the C matrix. So I set up this recursive procedure. Right, again, from the slides, of course, in the slides we call the recursive procedure. To calculate the C matrix was in equation 50. Right, so this we basically now bring to MATLAB. So initially we need to initialize the C matrix. I'll get to the F matrix in a second. Let's just first go to the C matrix. Initialize the C matrix, I initialize it to the edit. I, E, Y, E in MATLAB is the identity matrix of dim1, where dim1 I had defined before as being the number of rows of the image. Right? A and B are both squared, in our case 3 by 3. So dim1, of course, in our case is going to be 3, but this is more general, also going to work for other square matrices A and B. I set a convergence criterion. We had seen the other day when we calculated eigenvalues, eigenvectors in MATLAB that the precision that MATLAB claims is up to the 16th decimal digit. So I just put this a little bit above that, the convergence criterion, as 10 to the minus 15. Super small, I hope we can agree on that. And then I say I'm going to iterate on the subsequent loop until the sums across all rows and columns. Sum of sum means I first sum across rows, then I sum across columns. So the sum across all entries of the absolute value between the C matrix in the I plus first step is the same as in the I step. Right? So this is a very tight convergence criterion. And just iterate on it as we discussed. I minus B times the inverse, right? This backward slash was, remember the shortcut for the inverse, times A. If it doesn't converge after 1,000 iterations, it will tell us so, so that we don't wait forever. Now include the F matrix in this loop. Why? Because remember the F matrix was defined as I minus B times the inverse times B. So if I also iterate on the F matrix, it may help me to further learn about the C matrix in subsequent iterations, and therefore I include that in that loop as well. Not a strict necessity that we do it here, right? We define F as I minus B times C inverse times B, with the C matrix that we just got out of the previous calculation in row 53, right? We enter that here into the calculation of the next F matrix. Also need to initialize the F matrix, set a convergence criterion for the F matrix, and just for the F matrix the same as for the C matrix. To check convergence, I sum across all elements in the F matrix between two subsequent iterations, and that has to be less than 10 to power minus 15 as well. So very tight convergence criterion. And that's going to give us the C matrix. We'll display the number of iterations, and we'll display the difference calculated according to grid 1 and grid 2 for the difference between the last two C matrices that we had in the loop. this double percentage sign in MATLAB is a section break. So I'll execute this now not as a whole, but at least I'll try to execute it in sections so that we can see the input step by step. So first section, of course, right, is just to do housekeeping. Now I need to create a bit of space again for the output. Right, so the command window, you see empty command window, nothing there. Well, go to the second section where we entered the model, right, and calculated the A and B matrices. So if I run that section, it will give me at the bottom, I need to create again a bit more space, the A and the B matrix. Please notice the following. These are sparse matrices. Sparse matrices are right matrices that have a lot of zeros. Those are so-called sparse matrices. The only non-zero column of the A matrix is the last column. Does that make sense? What is the last column multiplying? Remember, of course, that has to be the last element of the y vector, the interest. Indeed, what is the only variable that enters into our model in lag form? Only non-zero in N10, the lag interest. So that's why in A there's no lag output, no lag inflation, right? Because the only lag term that entered initially in the first order conditions is the lag interest. What about the structure of the forward terms? The first two columns, right? We have forward terms on output, on inflation, and that's also now reflected in the B matrix. Only the first two columns are non-zero, the last column is zero, because those future expectations are in output and inflation. That's A and B. Now let's calculate C, right? That's the crucial matrix. C and F, of course. C is the backward part, F is in the forward part. So creating a bit space again for the top, right? I do that section now where I calculate the C and F matrices from line 45 onwards. I just put my cursor into that section, say one section. What do I get? I get that I needed 22 iterations. I just made this arbitrary guess, right? That the C matrix is the identity matrix, and F is the identity matrix, just after 22 iterations. This may take longer for larger models, and that's again why this is actually still so many years later in active area research, because in very complex models, this scheme may not be the best to do. But here, right for this size of the model, it works perfectly fine. And you see that the convergence criteria are in the first one for C, in the magnitude is 1.7 rounded times 10 to the minus 16, and for the convergence criteria for F, 6.9 rounded times 10 to the minus 18. But 18 is beyond the level of precision of matter. I wouldn't read too much into that. But anyway, it converges fast, right? And now comes the highlight, displaying the C and the F matrices and the eigenvalues. A and B we already know, but I still display them again too. Right, so if we execute that and make once more a bit of space to scroll back up, you see again the A and the B matrices. We had looked at them already. What is the structure of the C matrix? Backward looking part of the model, again, only in the last column I have one zero. The only lag variable that enters is the lag interest rate. I don't get out of nowhere, in this reputations model, all of a sudden lag output lag interest rate. The only term is the lag interest rate. If we calculate the eigenvalues of that C matrix, right, these better all be inside the circle. And the only non-zero eigenvalue is C because it has 2 zero columns, because it only has rank 1. It can have only one non-zero eigenvalue, and that is 0.28. Stable in the background, right? It's like, the requirement for VR that the eigenvalues of the lag coefficient matrix are less than 1. Finally, what about the F matrix? First two columns are 0, once more reflecting that the only forward-looking parts in this model are the first two entries of the y-vector, future output, future inflation. What are the eigenvalues of this F matrix that we calculate next? There's a pair of complex conjugate eigenvalues, but if you take the absolute value of that, well, below 1. So this is a unique stable solution. The form of the solution is as we had seen in 53. Can I show you the case of multiple stable solutions where eigenvalues of F are outside the circle, where we must have martingale differences within the setting? Yes, last minute before the break. Just really, I think really. Last minute. Make a bit space again. We have a section on multiple stable solutions, right? What is the value that I change here of the parameters? You check in the beta, the kappa, same as before. If I y, I normalize to 1. But I have here less persistence in the interest rate, right? Before the persistence in the interest rate, rho R, as I call it here, before was 0.8. Now I have it at 0.1. Before the coefficient on 5 pi was 7.64 pound net, and now we reduce it to where is it? 0.3. So, what is the central bank? It responds less in terms of adjusting inflation, right, than our previous central bank. We went down in this coefficient. I should say in terms of long run reaction adjust for rho R, but let's just leave that out. Have a much smaller response coefficient, unexpected inflation. In the world of central bankers, you would call the central bank that we had before hawkish. Right? It's like a hawk. It sees the prey. And what is the name of the central bank that is in lines 89 in particular? Dogfish. Bird of peace. Gentle. Let's not adjust the one pulse rate too much. Gentle. Right, this is our new central bank. Let's calculate the C and the F matrix for that, and display it, of course, and that should now be in the results window. Just need to get back. Look like this. Where is it? Where's my command window hiding now? I managed to design too much for my own good. How do I get back to the command window? One of you knows too, all this has changed in 25A. This one? Yeah, that is okay. This way I got it back. So now let's make a bit more space in the command window again. Right now we have this new F matrix. This is still the previous output. a new F matrix that has one eigenvalue that is an absolute value larger than me. Right? So this will give me multiple stable solutions. Because not exactly the form in the right, so it's like that all eigenvalues of F are larger than 1. Now there's 1, but I will have a component in the solution that corresponds in structure to 50. So the general result that's known in modern economics, I'd say also since about the mid-late 90s, if a central bank is not very hawkish, but is relatively dovish in terms of having a weaker reaction on inflation in adjusting its monetary policy rate, this could lead to multiple equilibrium. And this may have been actually the European Central Bank, because after the global financial crisis, they didn't bring the monetary policy rate down to 0. They waited for a long time until the European debt crisis was well underway. And so you could describe their behavior as leading to multiple solving question takes some time. Let's take a break. Maybe just 10 minutes. So if we resume at 5 to 3, then we should have enough